Okay, it's my pleasure to welcome Travis Mandel from Oklahoma, who will tell us about bracelet bases or theta bases.
Hey, thank you. Thanks for inviting me, giving me a chance to tell you about this new work of mine with Fan Chin. We've been working on it for a while. Just finally got it posted last month. And thank you for giving me a chance to give the talk on Zoom. So I'll tell you about our proof that the bracelet spaces for cluster algebras from surfaces coincide with the theta bases of Grossack and Kilkin-Savich. And this is joint work with Fan Chin. Oh, my monitor just went. All right, still there. Just my monitor flickered. All right, so here's the setup. So we work with a surface, so a marked surface. So I'll call it sigma, which consists of two pieces of data, S and M, where S is a compact-oriented connected surface, maybe with boundary, and so being connected is not really necessary, just make some statements a little simpler. And then M will be a finite set of points in S that we call marked points. So here's just a few pictures. Here's a disk with 5 marked points on the boundary, a genus 2 surface with 3 marked points, and then a genus 1 surface with a couple marked points in the interior, and then some other marked points on the boundary, 3 boundary circles here. And we always require that the set of marked points is non-empty, and that each component of the boundary contains a marked point. And then there's a couple other conditions, like you don't want something that's too simple. Like you don't want an unpunctured monogon or a once punctured monogon, an unpunctured diagon. Basically, you need to be able to triangulate your surface using arcs between the marked points. So just a few kind of boundary cases that we avoid. And then, so you can see some of our marked points might be in the boundary, but we can also have marked points in the interior, and the marked points in the interior are called punctures. Okay, so now the skein algebra, that we associate a skein algebra to this surface sigma. So this is spanned over Z. Sorry, my monitor keeps flickering. It's very distracting. Just my cable.
I was going to say everything. Okay, now everything's good.
Okay. All right. So the skein algebra is spanned over the integers by homotopy classes of immersions of curves. So here, phi from gamma to S. So this gamma is a compact one manifold, so a finite union of closed intervals and circles. And then phi is an immersion of that curve, that one manifold, into the surface S. And we require that the boundary points of your curve map to marked points. So again, the curve, it's circles and closed intervals, and just the endpoints of closed intervals have to map to marked points. And immersions here, I should say these are immersions, homotopies. I should say these are homotopies within the space of immersions. So you can't, when going through your homotopies, you can't have a curve that has like a cusp in it come up suddenly. They have to stay smooth. And then we mod out by these relations. So we say that a contractible arc is equivalent to 0. Here's a contractible arc that ends at our mark point. A contractible loop is equal to -2. Here, this is contractible even after you remove the punctures. If you have a loop that surrounds a single puncture, so we call this a peripheral loop. We say this is equivalent to +2. And then maybe the most interesting relation, the skein relation, if you have 2 strands that cross like this, that's equal to the sum of the 2 ways that you can resolve that crossing. So this sum. And you should interpret all of these as local pictures, looking at just some piece of your knot or your curves. So we might have, this is part of some bigger loop, maybe. It's maybe entered some mark points. Yeah. So this is living inside some surface. So something like this, maybe. And then, right, so we get this module, the skein module, by taking these curves, modulo these relations. And then we make this into an associative algebra with unit using disjoint unions as the product. Okay. So using disjoint unions as our product, this becomes an associative algebra. The empty curve forms the unit, the identity. We're just going out of this slide. So I'm not sure why this is blurry. So this is just some examples of skein relations. Let me try and switch to another copy of this file. Okay, it's loading better here. I'm in a different program now, so I can't highlight. But so we have so here's a skein relation. So we have this one loop that starts at this boundary mark point, wraps around this hole and comes back. So we have that arc, and then we also have this loop that wraps around here, and they intersect at 2 points. And using the skein relation, we resolve, we can resolve those two crossings in two different ways. That gives us 4 curves, but one of them will have a contractible arc, and contractible arcs are 0. So we end up with 3 terms. This thing on the left here is equivalent to the sum of 3 terms. And then also using the skein relations, you can check that the Reidemeister moves are satisfied. I should say you have to use the framed Reidemeister moves. So remember I said you have to stay in the space of immersions when you take homotopies of your curves. So you can't just remove this this loop in this curve. And the skein relation actually tells you that this is equal to negative what you get by removing that loop. But if you have kind of a double loop, then you can remove the 2. So I can switch back to this program. All right, so now we have a nice basis, or well, there's a few nice bases for the skein algebra. So I'll start with the Bengel's basis. The main one I want to talk about is the Bracelet's basis, though. So with the Bengel's, say an element of the skein algebra, so some immersion of a curve. If this element has no crossings, no contractible arcs or contractible loops, and no peripheral loops, remember those were loops that go around a single puncture, then we call it a Bengel. Or we call it the element that represents a Bengel, or a Bengel's element. And it turns out that the Bengels form a basis for the skein algebra. So you can at least see that they span, because any of the curves that are described here, we had skein relations that would let you remove all of those. If you have crossings, you can remove those crossings with the skein relation. Contractible arcs we said are -2, peripheral loops are +2, contractible loops are 0. So you can remove any components like the ones here. So that at least shows that that the Bengels span. In fact, they're a basis. And now any Bengel, notice we can write it like this. We can decompose it into the disjoint union of all of its, all the homotopy classes of its components. And then I assume here that all the components Ci are distinct homotopy classes. And then I can, if I have like Ki copies of some component Ci, I can just think of that as Ci to the power of Ki. Right. So you have a bunch of distinct homotopy classes of components, and then if there's repetition, instead of writing that element, Ki times, you just write it once to the power of Ki. Right. So I want to explain where these ideas are coming from. I think if you haven't seen these relations, they might seem a little ad hoc, like they're coming from nowhere, but there's actually some good motivation for them. So here's I'll explain two areas where these relations come from. So first, look at moduli of local systems. So this interpretation's due to Falk and Goncharov. So they define space, they denote A sub sigma. They call this the moduli space of decorated, twisted SO2 local systems, or denote them L comma alpha on the marked surface sigma. So I'll explain what all these words mean. So a G local system, in this case, G is SO2C, a G local system L on sigma, this is a principal G bundle with a flat connection on the complement of the marked points. And a way to think about these, a useful tool for understanding these, is this fact that the set of isotopy classes, or the space of isotopy classes of G local systems on sigma, that's isomorphic to Hom from your fundamental group of the surface minus the marked points to G modulo G conjugation. And the way that this correspondence goes is just say that you have a G local system on your surface. Then for any element in your fundamental group, you can look at the monodromy. Use your flat connection to find the monodromy around a curve representing that element in your fundamental group, and that will be an element of G. So that gives you a way to associate to anything in your fundamental group, associate an element of G, and that element of G is determined up to conjugation.
By isotopic class, you mean isomorphism classes, presumably here, right?
So yeah, I should have said isomorphism class. Yeah, that seems right. Thank you. Right. So so that gives us this correspondence. So let's see. So these are that's where an SO2 local system is. What about decorated and twisted? So the decoration. So that's this part alpha here. The decoration alpha. So that's a choice of an element of SO2 mod U. So U is a choice of a uniponent subgroup. So we can just take U equals 1, 1, star 0. So a choice of maximal uniponent subgroup. And so if you do this, you can identify this SO2 mod U with the complex, complex number squared minus the origin, C squared minus the origin. So we're choosing an element in here for each marked point, M. And we require that this alpha is monodromy invariant, so in particular parabolic, it has trace 2 at each of the punctures. And we think of these, when we associate SO2 mod U to one of these marked points, we think of that as being, as coming from taking a fiber of this G bundle, and then modding that fiber out by U. So you can parallel transport then from one marked point to another. So that's our decoration, just these choices of these flags, basically, these SO2 mod U's, or vectors, I guess. Sorry, these aren't flags. These are vectors in C squared minus the origin. And then the twisting. So what this is basically we actually choose a local system not on S, or not on S mod M, but the tangent space to S minus M minus the 0 section. So we take the punctured tangent space to the surface. And this allows for a little bit more. So instead of only looking at the fundamental group of the surface, we get one more loop, one more generator for the fundamental group. We get the loop around the 0 section. We've removed this. So topologically, this is the same as the surface minus M times a circle times S1. So we could work with that instead. And then we require that the monodromy around that zero section is negative the identity. Okay, and that's what makes this twisted.
Can I ask a question?
Sure.
So I want to understand this condition of alpha being parabolic around the punctures. So maybe my question isn't going to be well defined because it's actually all occurring in this tangent bundle. But if I put in a curve, I forget what you call them, but a little closed loop, which is contracts to a puncture, contracts to a marked point. The local system, the monodromy is the only requirement is that it has trace 2, or should it really be the identity, or is that the same?
Sorry,
Sorry.
I think we want trace 2. I think.
Okay.
Okay. Trying to remember why this happens, but yeah, I think you can have other trace 2 things that happen here, I think.
Okay, and I guess that's your relation that the evaluation of these closed guys is just the number 2. Never mind. Sorry. I think I understand.
Okay. Yes. Sorry, I don't remember right now exactly what happens. That makes it have to be parabolic, but something like if
Okay.
basically generally there might not be any monodromy invariant elements here, and that's oh, sorry. Yeah, so all right, I think what's going on, I shouldn't say alpha is parabolic. I should say the monodromy around the puncture has to be parabolic in order for a monodromy invariant element here to exist.
Okay. Cool, thank you.
No problem. Let's see. Okay, I should move on because I'm just going to get confused trying to remember what happens here. So the right. So how does this connect to skein algebras? So basically, the Falkengantra found that the skein algebra of sigma consists of functions on this moduli space. So given a loop in your surface sigma, what's the corresponding function on the moduli space? Well, you can take the monodromy or homonomy around that loop, and then take the trace of that. And that will give you, some number, some complex number. So that's taking, given an element of your skein algebra, that's taking a local system. Different local systems will have different monodromies around this loop. And then, you associate this trace of the monodromy. What about for an arc? So if you have an arc gamma between 2 marked points M1 and M2, we can use parallel transport using our FET connection from the G local system. The SO2 local system, use this to identify the copies of SO2 mod U that we associated to the 2 marked points, M1 and M2. And then this alpha, this is giving us, so you have this declaration alpha at M1 and M2. This gives us vectors V1 and V2 in this SO2 mod U. So think of that as being in C squared minus the origin. And then since we're able to identify these 2 copies of C squared minus the origin using that parallel transport, we can think of these as being in the same space. We can take their wedge product, and that lives in lambda squared of C squared, this top exterior power, and you can identify that with just C itself, complex numbers. So basically, we take the cross product of V1 and V2 as essentially what we're doing here. And now a couple of subtleties to point out. Basically, why did we have the twisting? Where's that coming in? So if you take, so what if you take just a contractible loop? So I said that in the skein algebra, a contractible loop should equal -2. But it seems like if you take the monodromy around a contractible loop, that should be the identity, which is trace 2. And what happens is that a contractible loop, because we're in the twisted setting, the monodromy of a contractible loop is actually negative the identity. So that means that the trace of the monodromy around a contractible loop will be -2 instead of +2. And then the twisting also shows up with arcs. So we had a choice here. There's no real difference between M1 and M2. Like which one should be labeled 1, which one should be labeled 2. There's not a canonical choice. So how do we know? Why can we do this? Why isn't this only defined up to sign? Like if we did V2 wedge V1, it seems like we would get something different than V1 wedge V2. They would differ by a sign. And what happens is if we parallel transported from M1 to M2, and so therefore we did V1 wedge V2. If we parallel transported the other way, then we would do V2 wedge V1. And these two curves, if you parallel transport along one of these curves and then back along the other, you'll get minus the identity because you have to put these curves in the punctured tangent space. And so that you get that minus the identity, that sign change there makes up for the sign change from changing the order here.
Yeah, so I've usually seen like these modular local systems with without that punctured tangent space. So it's not a precise question, but is it so you like throw it in there? So it solves these sign issues, right? But like, is that kind of is there more to that construction, or is that kind of the utility of throwing in that punctured tangent space?
Yeah, so Falk and Gottschalk use that space. So I think if you work with I'll talk about a quantum version of the skein algebras in a bit. And
Okay.
there will be this quantum parameter Q, and if you take Q equals 1, you get back this skein algebra. If you take Q equals -1, then I think that gets rid of the twisting. I think you don't need the twisting then.
Okay, thank you.
Okay,
No
can I have
problem.
a question too?
Mhm.
Didn't you say that the twistedness is like if you go around the 0 section, then if that's the condition? I guess I'm wondering how that fixes the sign issue for any 2 points, because the thing you just drew of like go from M1 to M2 and then back does not have to like enclose the 0 section. I mean, maybe I'm misunderstanding something. I'm sure how that fixes it.
So so these are curves drawn in the surface, but I should really be drawing them in the.
Oh, right. Okay. So in the tangent, we change direction.
Right. Yeah. The way you get from a curve in the surface to the curve in the tangent space is you take tangent direction.
Plus
You
the
take tangent directions to the curve, assume you have a smooth parameterization.
Great. Yeah. Okay. Good.
Yeah.
Yeah. Thank you. I'm happy now.
All right. Any other questions? Right. So that modular local systems, that's one interpretation of the skein algebra. So there's another one I want to mention. So this one's decorated techular space. So techular space for us, I'll call it this type of sigma. So we can say this is Hom, well, I'll say Hom prime. I'll explain the prime in a second. So homomorphisms from the fundamental group by fundamental group of sigma, I mean the surface minus the mark points. So Hom from pi1 of sigma to PSL2R modulo PSL2R conjugation. And then the prime says that we only look at discrete and faithful representations, and the peripheral loops should be parabolic. And this parameterizes certain hyperbolic metrics on your surface sigma. Specifically, I think it's complete finite area hyperbolic metrics of constant curvature -1, which are geodesic on the boundary components and have cusps at the marked points. So parameterize this class of hyperbolic metrics on your surface. So that's techular space. Now this T of sigma will denote decorated techular space. So this L will be just a point in techular space. And then the alpha will be the decoration, kind of like before. And here the decoration means a choice of horocycle centered at each marked point. So I'll have pictures shown there on the next slide, but basically a horocycle will be a curve in your surface, which is perpendicular to all of the geodesics that it passes through, or to all of the geodesics coming out of this marked point. Now, well, I guess in different settings, Penner or Falkengantrov or Fomin and Thurston observed that the skein algebra can be viewed as giving functions on this decorated technical space. So how this works. So if you have a loop, what we do just like we did before, if you have a simple non-contractible loop, you can take the monodromy. So remember, we have this associated element of PSO2R. So that's what this monodromy or holonomy is. And then the trace of that, right? So we take the trace of that element, but this is something in PSO2R. So you have to pick a lift to SO2R. And then I write this plus sign to mean use the lift that makes the trace positive. So that's just like before, just these traces of monodromies. What about for an arc? So given an arc gamma, so let's let L sub gamma denote the signed distance between the horocycles at the endpoints of gamma. So here's a curve gamma. It ends at these two red marked points. And the little red dashed circles or a half circle, those denote the horocycles that our decoration gives us at those marked points. And then L gamma is just the length of this part of gamma, the part between the horocycles. That's the length with respect to your hyperbolic metric. And see, and I should mention if so I said it's the signed distance. What I mean by that is, suppose that I chose my horocycles a little bit differently, like a little bit bigger. So now L gamma, I would look at the length here because the horocycles are crossing each other now. And we would count this as negative length. So when your horocycles, sorry. Uh-oh. Am I still here? Okay. Sorry about that. I reached up and hit my keyboard cover. All right. So right, when your horocycles cross each other like this, you count the distance as a negative distance. And then we define L sub gamma to be we define lambda sub gamma, we call this a lambda length, to be e to the L gamma over 2. So e to this length over 2. So this gives you some real number. It could be any real number associated to this. So we're getting functions from this decorated technical space to the real numbers. And it turns out these satisfy the skein relations from before, these functions.
Is there a reason why we don't want that to see even whole number lengths? Or well, oh, never mind. What am I saying? There's no I. Okay, never mind.
Okay. So I'll get back to the skein algebra now. So we talked about the Bengals basis earlier. Now I want to talk about the Bracelet basis. So remember that we said a Bengal you can think of as a disjoint union of homotopy classes of distinct curves Ci raised to powers Ki. These are positive integer powers Ki. And given one of these, we'll have an associated bracelets element. So we'll denote it basically the same way, but all right, instead of Ci to the Ki, all right, Ki Ci in these brackets. Now I have to tell you what that bracket, what that angled bracket Ki Ci means. So if gamma is an arc, then this angled bracket K gamma just means gamma to the K, like the element associated to gamma to the kth power. So it's the same as the Bengals element in that case. If that was a loop, though, we do something different. So when that was a loop, KL will be represented by a loop which wraps around K times parallel to L and then closes back up. So it self-intersects K minus 1 times. So I can draw this. So if we have a loop, so if this is our L, then KL would be something like this. I think I should have done that around the back. So yeah, something like that. And it looks like this crosses itself at 1, 2, 3, 4 points. So I think there should be 5L. 1, 2, is that crossing there? No, maybe that's 4L. I think I cover that up. So I think this is wrapping around 4 times, then closing back up. So this would be 4L. Right, and so then this would be the associated bracelets element. So again, the bangle, you would take like k distinct copies of the loop. With the bracelet, you just keep wrapping around parallel to the loop k times, and then close back up. So in terms of these local system, or this like moduli local systems picture, the bracelet was out of the k. We think of that as you take the trace of the holonomy around L and then raise that to the kth power. But with the bracelets, you first, if you go around your loop k times before taking the trace, you can think of that as you take the kth power of the holonomy and then take the trace. So the difference is just, do you take the kth power before or after taking the trace? Now, in terms of, all right, and you can understand this algebraically. There's a polynomial called the kth Chebyshev polynomial of the first kind, to note that T sub k. So this bracelet KL, that's TK of the element L. So TK, this is the polynomial such that if you have numbers lambda and lambda inverse, TK of lambda plus lambda inverse will be lambda to the k plus lambda to the negative k. So if you think of lambda as being, or lambda and lambda inverse as being the eigenvalues of your element of SO2, you can see how how that comes from this relation, or how it relates to that. The kth power of the holonomy, your eigenvalues will be the kth power of the original ones. So you get this relation. And this idea to use Chebyshev polynomials like this actually goes back to the 90s paper by Froman and Gelka. Okay, so that gives us the bracelet's basis. I want to mention now there's also a quantum version of all this. So this is due to Greg Muller and building on ideas of Kaufman. So if sigma is an unpunctured, or if sigma is unpunctured, so our marked points are all on the boundary, then we can define this quantum skein algebra. So to note this sk sub t of sigma. So instead of being an algebra over Z, it'll be an algebra over Z adjoined t to the plus minus 1, this Laurent polynomial ring. So in this setting, instead of working with these immersed curves, we work with links, which basically means whenever 2 strands cross, you have to remember which one is on top and which one's on the bottom. And then the skein relations become these quantum skein relations. So there's no punctures here, so we don't have the peripheral loop anymore. We still say that a contractible arc should equal 0. A contractible loop now, before we said it was -2, now we say it's negative q squared plus q to the -2. And, I should say, here I'm using q, up here I had t. Basically t is a square root of q. That's the relation. So yeah, contractible loop is negative of q squared plus q to the -2. And then the skein relation becomes this Kaufman skein relation. So here we have to use that the surface is oriented, and we have one loop crossing on top of the other. And then when you resolve your crossing in these 2 ways, one of the ways you multiply by q, the other by q inverse. And I have never managed to remember which one gets the q, which gets the q inverse. I have to look back at that every time. So now we can take products here. So remember, the product for the skein algebra was just disjoint union. So here we use the superposition product. So to do x times y, we do the disjoint union of x and y, but we have to specify which curves are on top. So we say that x always crosses on top of y, because there are links now. And then we have this extra t to the k factor. So that k, this is just a signed count. So it's the signed number of times that arcs I from your first curve x and arcs j from your second curve y share an endpoint. And what's signed about it, what's signed about it is we count with the sign +1 when I is clockwise of j at the endpoint, and -1 if I is counterclockwise of j at the endpoint.
So we've oriented the boundaries, or is that?
The surface is oriented.
Oh yeah, okay, yeah, you look at okay.
Right.
And then the negative on that quantum trace for the. So are we still looking at the puncture tangent space? Like there's a negative for the circle unit or the quantum dimension, right?
So I think that if you let t equal -1, then you don't need the twisted modulus. That's
Okay.
my understanding. I'm not 100% sure on that, but that's what I've heard.
Okay, so thanks.
So now, so Dylan Thurston looked at sorry. So he defined bracelet spaces here. So quantum bracelet spaces. So the elements, again, we'll write them like this just disjoint union of these angled brackets Ki, Ci, but now these will be in this quantum skein algebra. And for arcs, it's defined just like before. You take the arc to the Kith power, and for loops, this wrapping around K times and closing up approach doesn't really work, but we can do this. We use this Chebyshev polynomial approach. We define this angled bracket KL to be the kth Chebyshev polynomial of L. Okay, so so this bracelet spaces and quantum bracelet spaces is what I want to see theorems about. So now I need to explain the cluster algebra structure on these things. So need to talk about triangulations. So a triangulation of sigma, this is a maximal collection of non-homotopic arcs which intersect only at their endpoints. Here's a couple triangulations of a pentagon. So you can think of that as a disk with 5 marked points on the boundary. So there are 2 interior arcs, and then the 5 boundary arcs, which would just be the blue arcs, the boundary components, boundary strings themselves. And in general, given a triangulation, you can always produce a new triangulation by flipping one of your arcs. So if you have an arc gamma, that forms the diagonal of some quadrilateral, and you can flip that, or you replace that with the other diagonal of that quadrilateral, call that gamma prime. So we actually did that up here. So this arc, that's a diagonal of this quadrilateral. And then when we flip that, so here's the same quadrilateral, and then the flip is now this arc. And now the skein relation that we saw before, that gives us this Ptolemy relation that if we do gamma times gamma prime, that's equal to, so I have to write what A, B, C, and D are. So A times B plus C times D. So gamma times gamma prime is equal to A times B plus C times D. That's just immediately from the skein relation. So we always have these relations. So we have all these different triangulations, and the arcs from adjacent triangulations, like adjacent meaning you can flip from one to the other. Arcs from adjacent triangulations are related by these relations, these Ptolemy relations. So this gets us to the cluster algebra structure. So given a triangulation, delta, consisting of arcs gamma 1 through gamma n, we can consider this this algebra Z adjoined gamma 1 to the plus minus 1 da 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 gamma n to the plus minus 1. So this a torus algebra, because like the spec of this would be an algebraic torus. So sorry.
So if our sequence ahead has the ratio of two consecutive terms coming to 1, then we cannot have 3. And so it cannot be produced by WT.
Your sound quality is not very good. I can't understand.
So okay, so number 3 is out of the question, right? Number 3 depends on like so the question is, can we do 1 and 2, right? Can we satisfy 1 and 2? And the answer is yes.
Maybe you could type the question. Maybe that's the right thing to do.
Yeah, sorry, I'm still having trouble. While you type, I'll mention there's a fact that in general, the Skane algebra any element of the Skane algebra can be written as an element of this ring for any triangulation. So the Skane algebra can be realized as a subring of this A delta, no matter what triangulation delta you use. So you can think of these different triangulations as giving different coordinate systems for the Skane algebra. And these different coordinate systems are all related to each other by these Ptolemy transformations, or these Ptolemy relations that we saw here. So this is what gives the Skane algebra the structure of a cluster algebra. I haven't said what a cluster algebra is, but basically it's a certain type of algebra that you define in this combinatorial way, where you have a bunch of different coordinate systems, all of them being these Laurent polynomial rings. And given one, you can mutate with respect to a number of the different variables. And mutation is basically just this change of coordinates, this change of variables thing you do, which generalizes that Ptolemy relation. So the clusters here, the different coordinate systems, those correspond to the triangulations. And the mutations are the Ptolemy relations. So now so the Skane algebra has a cluster algebra structure, and Greg Moeller showed that the quantum Skane algebra has the structure of a quantum cluster algebra. In the quantum setting, it's similar. Your mutations, you have quantum mutations, which are similar, but you have to put extra t's in the right places. And also, instead of working with this A delta, you work with this, where you have your coefficients are in this Laurent polynomial ring, this Z adjoined t to the plus minus 1. And then this is actually not commutative. Like if you do gamma 1 times gamma 2, that might be something like q times gamma 2 gamma 1. So that corresponds to in our superposition product earlier, we had like x times y is t to the k of x disjoint union y with x on top. So that t to the k corresponds to some extra, basically the order matters. You have some extra powers of t that show up when you do products here. So that's called the quantum torus algebra. So did the question get in the chat? No. Sorry, I wasn't able to understand.
Yeah, you can also email me maybe.
Okay.
And I can pass it on.
Okay. All right, so there's some nice, positivity properties that people study in the context of cluster algebras. So suppose that as we say that an element F in the Skane algebra or the quantum Skane algebra or a cluster algebra is positive an element F in the Skane algebra is positive in the cluster A delta if all of its coefficients are non-negative integers, or in the quantum setting, Laurent polynomials with non-negative integer coefficients. And then we say F is universally positive if it's positive in every cluster. So for any triangulation, we're getting an embedding in an embedding here, and we're saying that, or we're getting this scaling algebra as a subring, and we're saying that all of these subrings, you always have positive coefficients for F. And now if you have a non-zero element F, we say that F is atomic if it's universally positive and it cannot be decomposed as a sum of two other universally positive elements. So these are like the extremal generators for your cone of universally positive elements. Kind of the minimal set that such that any universally positive element can be written as a sum of these. Now a basis, and we say that a basis is atomic if it consists precisely of the atomic elements. So Falk and Goncharov conjectured that cluster algebras should always have an atomic basis, the atomic element should always be a basis. Turned out that's false. Lili and Zolovinsky found that often the atomic elements are linearly dependent, but there's a modification I'll talk about soon that makes it true. Basically, you need more charts. It's not enough to just look at clusters. You have to use what I call the scattering atlas. All right, so there's another notion of positivity called strong positivity. So what this is, so given a basis of elements Fi, the structure constants are the numbers C, I, J, K, such that if you do Fi times Fj and write this as a linear combination of the Fk's, Cijk is the coefficient of Fk here. And then we say a basis is strongly positive if all of these structure constants are non-negative integers, or in the quantum setting, Laurent polynomials in T with non-negative integer coefficients. Okay, so now here's some big positivity conjectures. So Falk and Goncharov conjectured that the bracelet spaces should be atomic, and Doe and Thurston conjectured that the quantum bracelet basis should be strongly positive, and then naturally one would also conjecture that the quantum bracelet basis should be atomic. The classical bracelet basis should be atomic, so should the quantum one, and then atomic would imply strongly positive. It's not hard to show that. So basically, these conjectures will follow as corollaries of the main result that I'll get to in a couple slides. So first, I have to mention the theta bases. So I've spent 16 slides telling you what the bracelet bases are. I'll give you one slide on the theta bases. Fortunately, I kind of have to pick one to give you details on. So Grossack and Kielin-Kinsevich found that all cluster algebras, in some sense, they admit a basis of theta functions, which are universally positive and strongly positive. Their construction comes from ideas in mirror symmetry, especially the Gross-Siebert program. So they use these combinatorial gadgets called scattering diagrams, and then these theta functions, these theta bases, are defined in terms of certain counts of something called broken lines. So that's another combinatorial gadget related to the scattering diagram. So I won't define these, but I'll do an example where I'll at least draw some pictures of these, so maybe give some idea of what these are. And basically, these broken lines and scattering diagrams, these are supposed to be telling you about certain counts of holomorphic disks. So like some sort of like Gromov-Witten number or logarithmic Gromov-Witten number type count. They managed to make it all combinatorial instead of some more difficult Gromov-Witten stuff, so that you can actually work with it a bit more hands-on. And I found that this theta basis is atomic, not for the cluster, or not using positivity in terms of clusters, but atomic with respect to the scattering atlas. So I mentioned you have these scattering diagrams. These will basically be a bunch of walls that cut some space into chambers, and some chambers will correspond to the clusters, but there will be additional chambers that give you more local coordinate systems. And you need to look at positivity in all of these local coordinate systems for these to be atomic. Then I have a result from a few years ago with Ben Davison. We found that the quantum cluster algebras admit quantum theta functions, a basis of quantum theta functions, and these are again strongly positive and atomic with respect to the scattering atlas. And now, by the result of Yuri-Kuza, it actually turns out that the scattering atlas for cluster algebras from surfaces, the cases that we're looking at now, this turns out to be the same as the cluster atlas. So this issue I mentioned, that you need the scattering atlas instead of the cluster atlas, for these skein algebras, that doesn't matter. They're the same. I should say, except for a once punctured closed surface. Those cases are a little different. Jan had looked at this in her thesis, Yanzu, in the case of the once punctured torus, you have kind of two copies, or you kind of have two cluster structures there. In fact, for any once punctured closed surface, you have two cluster structures. But in other cases, you only have one, and that exactly matches up with the scattering atlas. So now the main theorem, main result with Van Chin, is that the quantum bracelet basis coincides with the quantum theta basis. So then, as an immediate corollary, the quantum bracelet basis is atomic and strongly positive. Okay, so I'm going to explain a bit where this comes from. So I'll start with an example, kind of the simplest, interesting example. So this is the twice marked analyst. So we have an analyst with 2 marked points on the boundary, a pair right here. Then these two curves, gamma 1 and gamma 2. So gamma 1, gamma 2, together with the boundary arcs B1 and B2, give you a triangulation here. And over here, I've drawn the corresponding scattering diagram. So I should explain what this is. So for these two interior arcs, gamma 1, gamma 2, we associate to these two, we call them initial walls. So these are some hyperplanes, or just lines in this case, and they have some function attached to them. So the functions here, so I should say some notation. This I write z to the AB to mean the element gamma 1 to the 8th power times gamma 2 to the bth power. And so now I attach these functions 1 plus z to the 0, 2 or negative 2, 0 to these initial walls. Those numbers 2 and negative 2, those are just the number of triangles that gamma 1 and gamma 2 share. So we have one triangle I'm highlighting now. Then the other triangle would be this one, purple one. So they share these two triangles, and then each one, gamma 2, comes immediately counterclockwise of gamma 1, and that tells you what sign to count with to make one of these -2, the other +2. So we get these initial walls, and then you add a bunch of additional walls to make the scattering diagram satisfy this consistency condition that Gosak and Kilkin-Savich have. And you can see that there's infinitely many chambers here. And related to that, there are infinitely many triangulations of this analyst. They all come from den twisting, the one I drew here. So you could take take a loop going around here, and you can just den twist this triangulation either direction by that loop over and over and over again. And if you den twist one way, you go from this initial chamber, that corresponds to going from this initial chamber to this one, this, or if you den twist the other way, going around this way. So basically every triangulation corresponds to a chamber here. And then we have this one kind of limiting wall, this one where the rays bunch up. It's kind of special. And then we claim that theta sub k negative k. So so I haven't said theta functions are associated to lattice points in this plane where the scattering diagram lives. So you can take a vector k negative k going this way, vector like this, k negative k, and there's a corresponding theta function, and we claim that theta function corresponds to this loop with weight k. So K times the loop and the analysis. And this can pretty much be checked explicitly. Well, at least the weight one case isn't hard to check explicitly, and you can also get higher weight. So there's, as I mentioned, in the theta function construction, you have to count broken lines. In this case, we have these 3 broken lines. I haven't told you what broken lines are, but hopefully drawing a picture gives some idea that there are these like piecewise straight lines that are allowed to bend when they cross walls, and there are certain rules about how they can bend. And then you look at kind of where they end. You can look at kind of the final directions, the directions that they came from, and that tells you the exponents of some the corresponding monomials. So this tells us that the theta function in kind of the initial cluster, the initial triangulation, can be expressed as this sum of monomials. You can check that the loop satisfies that too, and prove that they're equal. So now I want to give a kind of a key idea for the proof, just because I think it gives an idea. Well, it's an important idea, and I think it kind of gives you an idea of how we did this. So the key thing is what we call the gluing lemma. So we show that if you know that a bracelet beta in a surface sigma is a theta function, and then if you take 2 boundary arcs of that surface and you glue them together to make a new surface sigma prime, that bracelet beta will still be a theta function. So the theta functions are unchanged under gluing. You can cut your surface into pieces, prove that your loops or whatever are theta functions on the pieces, and then automatically they were theta functions on the original surface before you cut it down. So this lets us show, if you take a loop like this, if you take a loop and you can cut it out using 2 arcs, like these, this arc and this one. Well, these arcs cut out a twice marked annulus around your curve. So this is a twice marked annulus, and we just saw that this loop corresponds to a theta function for the twice marked annulus, so automatically it corresponds to a theta function in the original surface as well. And it turns out every loop, you can either cut out a twice marked annulus around it, or you can cut out something like this, where the loop is there's only one mark point on the boundary, and then the loop is homotopic to the boundary like this. And then these cases take a bit more work, but you can show here again that the loops are theta functions. And then once we know the loops are theta functions and show that the weighted loops are theta functions, and it's already known arcs are always cluster variables, which are always theta functions. Then we just need to show that their products are still theta functions. So that's kind of the strategy we take to prove the main result. And then just a couple of final comments. I want to mention we also prove kind of a dual version of our result. So Falk and Goncharov have this what they call a cluster Poisson manifold, where you look at moduli spaces of framed PGL2 local systems. So this has kind of a dual type of cluster variety structure. They call it a Langland's dual cluster variety or cluster Poisson manifold. And then Falk and Goncharov in the quantum setting, Allegrady-Kim, using this construction of Monahan and Wang, they described an analog to the bracelet spaces here, and we find that this again coincides with the quantum theta basis in that setting. And then last comment, and I promise I'll stop. So there's one kind of lie I've been telling, one thing I've been brushing over. When your surface has punctures, if you really want to get the full theta basis, you actually have to also consider tagged arcs. So a tagged arc, basically it's an arc where at punctures you're allowed to draw this little hourglass to show that it's tagged or notched there. And so Fomin, Shapiro, Thurston, they looked at these. They show that these tag arcs correspond to some addition. If you want your cluster variables to correspond bijectively to arcs, you need to work with tagged arcs. And Fomin and Thurston showed that tagged arcs satisfy this, what they call the Digon relation. So basically, in this picture, gamma times gamma prime is equal to alpha plus beta. So that lets you see how these include into your algebra. And then we can extend the bracelet spaces to get the tagged bracelet spaces by allowing tagged arcs. And this is what we show actually coincides with the theta basis. And then there's one last caveat. If you're looking at a notched arc in a once punctured torus, then actually, k times that notched arc won't be a theta function. It'll be 4 to the power of k times a theta function. And I should mention Yanzu's thesis. This is the case she looked at, this once punctured torus, and that was useful for coming up with exactly what this factor is here. Right, so we find this, and then you can ask, why is this one case different from all the others? And we think we know why. So we think that Bridgeland's stability scattering diagram, Tom Bridgeland has another construction of scattering diagrams based on representations of quivers. He calls it the stability scattering diagram, and it seems like maybe this is actually the right scattering diagram to use here, and that for the once punctured torus, we think that you get this one extra wall in the scattering diagram that kind of separates the two cluster complexes, and this one extra wall would contribute this 4 to the k when you cross it. So we actually have kind of another paper we're working on now with an undergrad student of Fans who are trying to prove this. So that's it then. So thank you.
Oh yeah, thank you, Travis. Any questions? Yeah, go on.
I was just going to ask, is there a way to do skein algebras for non-orientable surfaces, or does something go horribly wrong?
I've never seen someone trying to do that. I don't know. My guess would be that something goes horribly wrong, but I don't know. I've never seen that attempted. I don't know.
So on the skein picture, and okay, you have all these punctures and stuff, so maybe in certain settings, like it would seem a little more obvious, like how to see like an action of a mapping class group, right? Because you just have these holonomies and you just mess it up. Is that like manifested at all on the other side?
Yeah. So the mapping class group. For cluster algebras, there's something called the cluster modular group, which at least contains the mapping class group.
Yeah.
In these cases, and this cluster modular group acts equivariantly on the theta functions. So it acts on the algebra in a way that maps theta functions to theta functions, and then it kind of maps on the index set for the theta functions in a way that is compatible with that. Okay. So we actually use that several times in our paper. That we'll show that we'll look at what happens when we den twist our elements in the skein algebra, and then that that tells us something about the corresponding theta functions. And what like if you den twist by a loop many times, kind of in the limit, you get closer and closer to the kind of the vector that corresponds to the theta function that's supposed to correspond to that loop. So we use that to kind of sometimes with our scattering diagram, we kind of want to be in a certain kind of far off chamber, and we use these den mapping class group stuff to get into the chambers we want to be in.
So then, like on the surface side, so the cluster, these charts are given using like triangulations, right? You said each one you had. And so you're saying you could define somehow this mapping class thing from, I mean, basically this triangulation is like very local, right? Where as compared to like kind of this more global thing on the surface, like this mapping class group. It's a very big question, but so you're saying like you can define this cluster mapping class group from Okay, I guess there's local information, but then you glue it together. But
Yeah, so the definition of the cluster modular group is something like it's a sequence of mutations followed by, so that takes you to another cluster, and then followed by an isomorphism from that cluster back to your original one. And you always have these associated to things in the mapping class group.
okay.
And I mean, you can see the mapping class group will take a triangulation to another triangulation, so that's to another cluster.
Okay. Okay. Any other questions?
Yeah, can I ask? So as far as I know, this fog puncture of story has a high rank analog, right? You can do it for SLN at least, and do your results carry over to high rank, or might they?
No, so that's definitely a direction I'm interested in, but that's in higher rank, it's not clear, what is the right basis, or how do you write down what the right basis should be. And there's some ideas, at least in some cases, but yeah, I don't know how to do higher rank yet, but I want to look into it. I do know some of our techniques will extend to higher rank cases, like the mapping class group stuff. We can use that. The gluing lemma, the way that we prove the gluing lemma in the paper with Fan will not extend to higher rank stuff. But I have another paper in progress with Tim McGee, Greg Moeller, and Mandy Chung, where basically some different, totally different techniques, looking at what we call tropical theta functions to show that basically a gluing lemma will work in the higher rank cases. So, at least some of the key steps will extend, but then there's some other stuff that will be very hard still to figure out.
Okay.
For the skein algebra picture in the higher rank, will you need to somehow color the curves, or
So let's see. So in higher rank, instead of using just a triangulation, you use you take a triangulation for like SLN, and then for each of those triangles, you triangulate that. Maybe I can. So for like SO2, you'd have something like this. Then for SO3, you have to get these more complicated triangulations.
okay.
And it gets to be a much more complicated picture, and I don't think let's see. So there are things called there's the web basis that in like the SO3 cases, and I think it's expected that the web basis will not quite be the theta basis, but they should be closely related. There's something called the MV basis, which I think is expected to to coincide with the theta basis. I don't really know much about that though, but yeah. Yeah, definitely something I want to look into in the future. That'll take a while.
Yeah, any other questions?
Travis?
Yeah.
So can you say more why, like, if by looking at these tropical theta functions, it will help you prove that gluing lemma? Is that what you just said?
Yeah. Yeah. So
can you say more about it?
Yeah. So maybe you should actually talk later, because I feel like that's gonna take me off. Let me see if I can remember.
Oh, it's okay. I can email you later.
Yeah, so I think it will take me some time to remember the argument and explain it. So I think we should talk separately.
Yeah.
But
also, like, what do you mean by, like, for higher rank local systems, it's like not clear what basis you're looking at? It's like we don't know what the setup bases are, or we don't know, like,
we know what the theta basis is. I don't know what's the right analog of the bracelet basis. Like what sort of more like geometric or representation theory type of basis should coincide with the theta basis there. And so like Goncharov, Shen, I think have some stuff with have a construction of some sort of basis that would probably be the right thing using this like this MV basis thing. But I don't know.
What? But like assuming that like for higher rank local system, if your Betty moduli space is still like a cluster variety, don't we just have theta basis? So
Oh,
is
yeah.
that the question?
Yeah, or we do know we have the theta basis in those cases. We know that for all cluster algebras and for all these high rank cases, but like our result here is that the theta basis has this nice visual interpretation as this bracelet basis, and this bracelet basis has some meaning in representation theory or whatever else technical theory, and so we can say what. If you look at the theta basis for the SO3 moduli space or SO4 or whatever, what does the theta basis mean from the perspective of a higher technical theory in this representation theory viewpoint? Is there some nice way to draw like this element in this moduli? Like, this theta function corresponds to this thing in the moduli of local systems. And we don't know that interpretation yet.
So I mean, for higher rank local system, you will want to compare theta basis with whatever Goncharov and Shen constructed.
Yeah, I'm not. So I don't know the Goncharov Shen stuff well enough. That they have some very long papers. So I don't know the details yet. But yeah, I would like to compare the theta basis to some other basis that people know about and care about, or if there's not some other basis, construct a basis that you could convince people to care about, I guess. Let's see. Yeah, there's very few cases where people can say explicitly like this is what the theta basis is and how to understand it. Like there's rank 2 cases, there's the greedy basis, and then in simple cases the theta functions are just the cluster variables. And now we can say for cluster algorithms surfaces the theta functions are the bracelets. But then in like any other case, it's just this broken line construction, and then what does that like? What's the intuition behind a theta function then? Like, what does it tell you about the geometry of or the representation theory that motivated your space or your cluster algebra? I guess there's the original motivation for cluster algebras was this Lustig's dual canonical bases. Fomin and Zovinsky wanted this combinatorial way to understand these dual canonical bases. And so initially we'd hoped that the theta basis would be would coincide with that dual canonical basis. It seems it's actually different from that. It's probably this MV basis. And then the dual canonical basis, I think, would be like there's one that would be the bracelets basis. Oh, sorry. I think that would be the band's basis, and then the Bingos basis would be like the triangular basis or something. So there's so Fanshin has some work on this, like the band's basis I didn't talk about, but that's another basis for these surface cases that should correspond to the dual canonical basis. And then something called the triangular basis should be I don't know, something else from representation theory. So we're just working on what do the bracelets correspond to.
But even in rank 2 case, like rank 2 local system, I forgot, like, do people know that theta basis coincide with for Goncharov basis?
So the Fock-Goncharov basis for the SO2 cases, that's the same as the bracelets basis.
That's not.
Yeah, that's not. So I should have mentioned that. Yes, they I did sort of say so their basis. They think of it as these traces of holonomi's. Use that approach, but that's the same. That's the same as the bracelets approach. Their basis is exactly the same as the bracelets one.
Because they're both considering like trace of the holonom.
Yeah. Yeah.
All right. Well, let's thank Travis again.
Thanks.